Good morning, Chem 20s. We're going to start our first real lesson of Chapter 4, Gases. Our lesson today is going to be on the kinetic molecular theory. So let's get started. So, little review from previous courses, probably grade 8, is we want to look at the difference between solids, liquids, and gases. Although this chapter is mostly about gases, I find it's very hard to look at gases if you don't understand solids and liquids as well. So remember, in a solid, this is when we have tightly packed particles. This is where there's that repeating pattern of a crystal. This is where, if we think of a Lego brick, it's got a definite shape. I put it in a beaker, it stays a Lego brick. It's got a definite volume. Again, it stays a Lego brick. These particles are so close together, all they can do is vibrate. And we know they have zero to no compressibility because if you've ever stepped on a Lego brick, you know how much they don't give and how much they absolutely do hurt. Now, if we add a little bit of heat to a solid, of course, it eventually turns into a liquid. Liquids means that the particles are still close together, but that they do have a little bit more room between them so that not only can they vibrate like a solid, but they also can roll past one another, kind of like when you pour a liquid, how particles can move and they don't have the same spot in a beaker. If I pour it into another beaker, that particle that was on top can be somewhere else. So they have an indefinite shape, meaning they take the shape of their container, but they do have a definite volume. 100 milliliters in one container is 100 milliliters in another container. They can, of course, move past each other. And this time they do have a low compressibility. You can compress them a little bit. If you've ever taken a syringe and filled it with water and plugged it with your thumb and tried to squeeze it, you can get them a little bit closer together. But again, not much movement for compressibility. Gases, however, are very, very different. And so I always think of them in like a balloon. There's lots of spaces in between them, lots of movement in between them. They not only vibrate, they can roll past one another. And of course, they can travel in a straight line until they either hit a side of a container and they bounce off, or they hit another particle and they bounce off and they travel in a different direction. You would remember the word diffusion. They diffuse to fill the container, therefore their shape is indefinite. They also diffuse to fill their volume of container, so it's indefinite. So I put them in something, they spread out until. So if I was to say I take, let's say, a perfume and I spray in this room, it's going to feel strong in the beginning, the smell in that area, but they're going to bounce and move out from areas of high and low concentration until they spread out in this classroom, which means the particles are so far apart. Ideally, if you walked back in here, you probably don't even smell the perfume because that's how big of difference the particle movement is in here. They're highly compressible. I certainly can take a container and I can squeeze it again. If I take that syringe and I plug the end, I can now compress it a lot further with this. Really easy to compress a gas. Okay, so I'm going to look at gases today and for this whole chapter. And when we look at melting and boiling points, we tend to think that they are stagnant. The boiling point of water is 100 degrees. That is not true. It's actually got a very, very huge connection between atmospheric pressure. So, for instance, in Medicine Hat, the boiling point of water is not 100 degrees Celsius, it's 97 degrees Celsius because the pressure is lower because we are above sea level. So again, these values that we know, 100 degrees Celsius for boiling, 0 degrees Celsius for melting, those are at sea level. When pressure is lowered, the boiling point is lower because it's easier for particles of the substance to spread out in the gaseous state. Now, this is just a fun little slide I found. I wanted it to be something that hopefully you would take the time to read, take a look at it. It compares lots of different high buildings or mountains. In this case, it's got the London Tower. It also has Mount Everest. Lots of little things for you to read. I thought some of you might enjoy this slide. Okay, so let's go back to gases. Okay, so I've got a perfect picture of gases here. It's got 6 particles bouncing around. Again, we're going to remind us that gases do take the shape of their container. That means they diffuse, and they diffuse and travel in a straight line until they run into another object or another particle. They are certainly highly compressible, and as the temperature increases, we should notice that the volume also increases. They spread out the hotter it gets. Now, here are by far, if it was me looking at the most important slide, this slide more or less sets up this whole chapter. When I am talking about pressure, we are talking about how often the gas particles hit the side of the container. When we are talking about volume, we are talking about the spaces between gas particles. When we are talking about temperature, we are talking about how fast the gas particles are moving in a container. And when we are talking about amount means chemical amount, that means number of moles in chemistry. And we are talking about the number of gas particles present in the container. On the right-hand side, you will see here's all of the units we're going to be using. We will be using atmospheres, millimeters of mercury, pascals, and kilopascals. We will be looking at liters and milliliters. We will be looking at Celsius and kelvins. However, when we do any calculations for gas laws, we must convert Celsius to kelvins. We will never substitute Celsius into the formulas in gas laws. And then last but not least, we will be using moles. Now, because pressure is so important in the first formula, I want to take a second and look at it. When we're talking about pressure, we are always talking about the number of collisions hitting the wall of the container. The higher the pressure, the more collisions hitting the walls of the container. The lower the pressure, the less of the particles hitting the walls. So we're talking about how often we hit the sides of the containers. Now, we've made some connections here on stuff you previously know. But again, for me, probably the most important connection we can make with pressure is unit conversion. So this is something you have to memorize. This is not going away. This is memorized 100% of the time. So let's see if I can get my pen here because it doesn't seem to want to give it to me the normal way. So our conversion, well, we should know that there's 1,000 Pascal in 1 kilopascal, because again, that would be on my conversion chart. Kilo going down to normal unit would be Pascal. Here's a connection you probably didn't know. 1 atmosphere equals 101.325 kilopascals. And here's another connection you probably didn't know. 760 millimeters of mercury equals 101.325 kilopascals. So this is what you need to memorize. 1 atmosphere equals 101.325 kilopascals. And that equals 760 millimeters of mercury. That is the connection we need. This is no different than knowing that there's 60 minutes in an hour, 24 hours in a day. That's the connection there. This is the connection here, which means if I convert all of these to one, you will see that 1 atmosphere is greater than 1 kilopascal. 1 kilopascal is greater than 1 millimeters of mercury, and 1 millimeters of mercury is greater than 1 pascal. Now, instead of having to calculate this all this time, to go, hey, if all these numbers were equal, 1, 1, 1, 1, which one is greater? You'll notice that there's a pattern. Atmosphere comes before kilopascals. Kilopascals becomes before millimeters of mercury, and millimeters of mercury comes before pascals. It goes alphabetically. So if I'm comparing 5 atmospheres to 5 kilopascals, I know that 5 atmospheres is greater. Now, what I would like us to do is I would like us to use our conversion factor from over here, and I would like us to do some conversions. We are going to have to do these all the time. This is a critical step. for figuring out pressure. So again, I'm going to do it the same way we always have. I'm going to write down 3.50 atmospheres. Now, the connection between atmospheres and millimeters of mercury is right here. So there is 760 millimeters of mercury in 1 atmosphere. So again, I set it up so that atmospheres is on top, atmospheres is on bottom. They're going to cancel out. So I'm going to take 3.50 times 760, and we're going to get 2,660 millimeters of mercury. Let's try another one. We have 100 kilopascals. I would like you to pause the video, try the next two, and then unpause the video when you're ready for the answer. Thank you. So to change, I know that there's 1 atmosphere in every 101.325 kilopascals. I set it up this way so that kilopascals is on the top, kilopascals is in the bottom. They cancel out. So again, 100 times 1, multiply the top, enter. Now we're going to divide by 101.325. And the answer is 0.986, yada, 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 atmospheres. So 0.98692326667. Big, lots of decimals there. That's in atmospheres. And the last one, we have 775 millimeters of mercury. Now, the connection between millimeters of mercury and kilopascals is 101.325 kilopascals in every 760 millimeters of mercury. Again, I set it up because millimeters of mercury is on top. I needed it on the bottom. So I'm going to take 775 times 101.325, enter, divided by 760. And my answer is going to be 103.325, yada, 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 kilopascals. I cannot tell you how important it is for this to be memorized. That is the expectation. That is not given to you. That must be memorized every single time. So please take 5 minutes, 10 minutes, whatever it takes you to get that conversion factor memorized. Thank you. Hope this lesson went well. Please rewatch it if you need to.